Morning, everyone, and welcome to the fourth day of the Data Science and Industry Student Workshop. Today, I'd like to present to you Dr. Collins Leke. He is a lecturer in the Department of Accountancy, and his research interests include the application of computational intelligence and artificial intelligence techniques to engineering, computer science, finance, and social science and medicine. And he will be discussing something which I think is an extremely important topic, which is the problem of missing data. So thank you very much. Please, Prof, we're waiting for you to take it away.
All right, thank you, Prof. Just so everybody knows what I look like, that's my face. So you don't think it's a robot talking, considering the current times for the industrial revolution and all. So like Prof mentioned, I'm going to be talking about missing data, which in the data science realm and domain, I consider missing data to actually be quite an important topic. Because imagine this, you have 100 records, and in those 100 records, 50 of them have missing data. So if you apply, which we're going to talk about later on, if you apply a conventional or traditional missing data technique, like your Listwise data deletion, that means you have 50, you delete 50 of the records from the 100 and you'll be left with 50. Now the question you ask yourself is are those 50 quite representative? Are they representative enough? So it makes sense wanting to address this missing data issue besides just using the conventional and traditional approaches to handle missing data. So we're going to ask ourselves, in this presentation, we're going to look at, okay, what is missing data? Then we're going to look at the mechanisms and some of the patterns of missing data. Then we're going to look at some of the traditional approaches. Like I mentioned, under normal circumstances, you don't want to use the traditional approaches because they come with their own drawbacks and pitfalls. So we'll look at traditional approaches to handle missing data, and then we're going to look at some advanced techniques for handling missing data. So we're just going to mention here a few of them, but there's more. We'll find, I'll look for the literature so that you can go through as well and read and just to further improve your knowledge on the topic. Now, we could ask ourselves, what is missing data? It's actually been a problem for many years. It's been an area of interest and research for several years. So what is missing data? Is basically a scenario whereby in your, I'm sure you've heard from the previous days, the presenters talk about probably the mentioned missing data, because it's a big issue. It doesn't lead to representative outcomes if you have missing data. Is your data representative enough? That's a key word. Is it representative? So you can avoid biases in your outcomes, in your outputs, and it's all based on the data, based on the information. So now, if we see here, it says missing data is a scenario in which some of the components or variables in your data set are missing. Ideally, it will be because you have variables which are the columns, you have records which are the rows. So in a record, you can have one or more missing. Of course, in a variable, which is a colon, you can have multiple missing, yes. But now we actually focusing on rows, which are your records. You can have multiple variables missing in your row or in the record. Now, with the presence of missing data, so having missing data in your data set, it produces basically a plethora, a variety of problems. So I will take a good example because I like using examples because it gives context. So if we're doing a loan application or credit card approval, so if you have some information missing, for example, everything was provided except your monthly income, monthly expenses. If that is missing, would you then be able to make a representative as a decision? If you have those two variables missing, would you be able to make a representative decision? The answer is probably going to be no, most likely going to be no. And it wouldn't make sense for you just discarding that record, that individual. You'd rather want to impute that missing information based on what you already have so that you can actually make a decision. Now, several techniques to handle missing data have actually been looked at and looked into. Some of them are traditional, some of them are not advised, some of them are more advanced, and they actually address the issue to an extent. So we're going to look at those examples later on. So this is for the participants and for my fellow colleagues. I consider you colleagues because we need to address this issue. It makes sense actually finding solutions to missing data rather than just implementing traditional pairwise deletion, listwise deletion, so deleting a record because there is missing information. So I'm going to call you my colleagues because we are going to address this issue. Now, missing data it's a problem that is encountered in the pre-processing stage of a data science task. That's the reason it's very important. So in the data science task, there's pre-processing. There are several stages. One of them being data pre-processing. And that's where you solve some of these issues like missing data. So it will make sense to actually look into the missing data. Can we, without involving human bias into the process, actually impute this missing data? So we're just going to take a couple of minutes and I would like to hear your thoughts on this couple of questions which one is asking. So what could be the reason for the presence of missing data in your data set? And could we get representative outcomes if there is missing data in our data set? So please feel free. You can drop your response in the chat, which is available. And yeah, let's have a conversation around this. There'll be a couple of other questions which I'll ask down the line because I just want us to interact and and I just want to hear my colleagues' views on this problem. So we're just going to answer this couple of questions. Please feel free to drop your answers in the chat function, in the chat box. Then we'll check and discuss. Thank you. Okay, perfect. Okay. Oh.
Okay, I have a question.
Just coming in. Yes.
I have a question. Okay, so by representative of missing data, it really depends on the nature of the data, right? Like if you have
Yes.
missing data if it's a financial data, then, either you take the average or the mean. And for instance, it's a biological data. If it's empty, then you can't just really take average, right?
Yes.
And then actually yesterday in Prof. Moniet's talk, he did some, not yesterday, sorry, on Tuesday. Okay, so he did some analysis using Excel. And what he mentioned was that in Excel, even if there was like missing data, there was a data, I mean, I haven't used it yet, but there was a data analysis feature where even if there was missing data, Excel still did the data analysis. So I think what he pointed out last time was like for Mathematica, when he used to analyze the data, Mathematica would just not converge, but Excel would. So yeah, so what is your comment on this one?
Okay, my comment on that will be, it's a good thing that we actually now have software that can handle such scenarios, such instances. But the question I'll ask myself is what it actually does on you said data analysis in Excel, is what it actually does what we want it to do? Does it actually get values which are what they should be, or even close to what they should be, if that makes sense? So hopefully they have actually included advanced techniques to handle missing data in Excel and not just the traditional. Because see later on, some of the traditional are using the median, using the mean or the average, which introduces biases into the estimates. And you want to actually avoid that. Because if you include biases, then your outcomes are going to be biased as well. You ideally want to eliminate this biases from the imputed value.
Yeah.
So
No, no,
hopefully,
it's just it's just that I don't yeah, I just it was my first time to see this feature in Excel, the data analysis feature.
oh, okay.
Yeah, and yeah, it's true in the comment. I haven't tried it, but yeah, someone commented as well that Excel probably won't handle big data. But I think Prof. Momonia's data last time was like 33,000 rows, which is big enough.
Oh, yeah. So yeah, the data analysis, I'm not sure how good Excel might be at handling big data, considering its size plus. Well, I consider big data to be size plus infrastructure. Because with the infrastructure, we can now host and store the data, and we can process the data, which has always existed. So okay, no, thank you very much. I really like that you brought that up. Excel can handle big data though. Yeah, I see the comment now. Yeah, Excel is limited in terms of the number of records or rows it can actually handle. That's why using advanced techniques like deep learning to handle missing data will actually help. And that's something we're going to see later on. But thank you very much. I like that view and the comment. Or anybody else, feel free. So that answers the Excel part. Yes, Excel is limited in terms of the number of rows you can actually, for lack of a better word, process. It limits you on the number of rows. And now if you look at variant data types, so besides numeric, you have text, it might have difficulties with that as well. So Excel not being able to handle big data, yes. Okay. Okay, so we're just going to move on and we'll look at these are just some of the reasons why data could be missing in your data set. And that will mean you need to do the imputation. So missing data, for example, if you're doing a survey, some of the participants might actually decide not to mention some information which is asked for. For example, age, which is normally something we don't use. Demographic information, age, race, and the sex of an individual. That's normally something we don't use, but in your data set, individuals might actually decide not to reveal. So that's a reason data could be missing. Then we could have issues whereby sensors actually fail in domains or areas that use the sensors. That will mainly be in your engineering sectors. So now if the sensors fail, then the information which they're supposed to report doesn't get sent to your database. So that information is missing. Then, now comment on the chat. Then another one is because of human error in the data entry process, some information might actually either be wrong or missed entirely. So these are just some examples of why missing data can occur in your data set. There are several other reasons for missing data in your data set. Hardware failure, which is linked to failures in sensors. And there are other issues that can arise that can lead to data being missing in your data set. Now, having spoken about that, let's have a look at some of the missing data mechanisms. So in 2014, I knew of 3 mechanisms, and now 2021, there are actually 4 mechanisms of missing data. So you have the missing completely at random, missing at random, missing by natural design, and missing not at random, which is also the non-ignorable case. So we're going to look at those different mechanisms of missing data. So missing completely at random, this scenario arises basically when the chances of there being missing data entry for a variable. So we're going to use the table below. So we have A1 to A7. So in this case, we're going to focus on A1. So when missing data entry for the variable A1, now let's replace A1 with, let's make A1 actually real. Because instead of just using a dummy variable, let's say make A1 real. So A1 could be your monthly income. Yes, so let's say A1 is monthly income. So when the data for A1 or monthly income is not dependent on the variable of interest itself, that is the monthly income. So when it sounds sort of counterintuitive, but basically we're saying when monthly income, that variable doesn't depend on monthly income itself. Just to provide context, and instead of using dummy variables A1, A2, A3. Now, what this basically means is the missing value is independent of monthly income itself. And let's take the table. Let's have a look at the table. In the table above, the nature of the missing value in the first row. So for A4, because we see there's the question mark. So if we look at row 1, A4 is missing. Everything else is present. Now, what this is basically saying is if we take a look at that first row, in A4, the data is said to be missing completely at random if the nature of this missing value does not depend on any of the other variables in that record or in that row, because rows represent records, columns are variables. So if the missing data in A4 in that first row doesn't depend on A1, A2, A3, A5, A6, and A7. Now, mathematically, missing completely at random can be expressed as we depict there. So using the probability function or depiction or description. So the probability of your missing data given the other values, more or less. So that would be missing completely at random. Now the other one, missing completely at random, that was the first. Now the other one is missing at random. So what missing at random says is, missing at random occurs if the chance of there being a missing value in variable A4 in this instance depends on all the other variables within the data set, but not on the variable of interest itself, that is not on A4. Now, we'll take the table again. So in the table which is depicted, the nature of missing value in A4 is said to be missing at random if the missing nature of the value depends on all the other available data entries. So it's very closely aligned to missing completely at random. And we can see that from the probability function written, where the probability of the missing value depends on the observed input values for all the missing data. So even for row 4 in our table, where A4 is missing, A5 is missing. So the traditional says, okay, delete row. We have 4 rows now, 4 records. Traditional methods say, for example, delete row 1 because A4 is missing. Delete row 4 because A4 and A5 are missing. Oh, we can also delete row 2 and 3 because A7 is missing. Now you're basically going from 4 records to 0. Why? Because your traditional method says, okay, if there's missing information, delete it. Delete that record. Which I'm not going to speak only for myself, but just thinking about it, it doesn't make sense going from 4 to 0. You'd rather want to find a way to impute that missing value, and then you have as much of the data available as possible. So I don't know if that makes sense, or I think this is somewhere we can actually, oh yeah, later on we're going to discuss here. But now those are traditional methods. They will basically say delete. In this case, one of the methods will say delete everything. As far as it does a missing entry, okay, it makes more sense in the traditional sense to delete it. Which, thinking about it, we're going to go from 4 to 0. And you don't want to do that. Personally, I don't want to do that. I need all the information possible to be able to perform a data science task. Because data science is all about information from your data. How do you then present information based on the data you have? The other missing data mechanism is missing not at random. So missing not at random is basically a scenario whereby the chances of there be missing data we'll take A1 again, which is monthly income, because we're going to change it from dummy variable to something representative so we can actually create a link. So the chances of there being a missing entry in monthly income is influenced by the value of the variable in monthly income itself, regardless of whether or not other variables in the data set are altered and modify it. So let's unpack that. So it basically says if there's missing data in A1, which is monthly income, it is influenced by the value of the variable monthly income of A1 itself, regardless of what happens anywhere else. Whether we make changes in A2, A3, A4, A5, and so on, or not, they don't have an impact on the variable A1 or monthly income itself. So at the end, provide a couple of references. These are pioneers. These are people who've been working in the missing data area for some time. So believe they know what they're talking about. So you'd see some references at the end. So in the case of missing not at random, the pattern of data which is missing is not random, and it is impossible to predict this kind of missing information. So it's difficult to impute missing not at random than it is to do the imputation for missing completely at random or missing at random, the other two mechanisms we spoke about. So this is the next point basically speaks to that, being the missing not at random scenario is the most difficult to approximate and model than the other missing data mechanisms like you're missing at random and missing completely at random. So coming up with a solution for missing not at random, I think a lot of people are going to be smiling and happy that there's actually a solution to handle this kind of missing data. Now, the last missing data mechanism is missing by natural design. So this is data that's missing for no logical reason, and the data is missing because it should not exist in the first place. So you'd see the last two mechanisms which are missing at random and missing by natural design. Then you actually sit back and think, okay, if we are saying the data is missing because it should not exist in the first place, imputing that data or coming up with a technique to impute that data, it already sounds difficult. Probably not impossible, but it sounds difficult. If it wasn't meant to exist, then how do you then impute such missing information? Especially if it cannot be measured physically. How do you then, something that's not meant to exist, how do you then impute such information? So right now, there is no known formula at the moment that helps in dealing with missing by natural design. And the reason for this is such data are relevant in the relevant data analysis, but they are impossible to measure. So then how do you impute such data? How do you handle such missing data? Now we're going to take a look. So those are the four missing data mechanisms. We're going to take a look at the missing data patterns, of which there are two. There's the arbitrary and there's the monotone missing data pattern. Now, arbitrary basically says missing data can happen anywhere, can occur anywhere in your data set. So if we look at the table, which is depicted, there's no sequence to the missing data. missing data happens randomly. In row 1, the missing data is in A4. In rows 2 and 3, let's take row 2, the missing data is in A1 and A7. Row 3, it's in A7. Row 4, it's in A4, A5. So it can occur anywhere. So that's what the arbitrary missing data pattern says. Your missing information can occur anywhere. There's no predefined. Let's say predefined way in which the missing data can occur in your data set. The other pattern is the monotone missing data pattern, which basically says the order of the variables is of importance and occurrence is not random, like in the arbitrary case where we saw missing data happen randomly. So if we take a look at the arbitrary pattern again, missing data happens randomly, while in the monotone missing data pattern, the occurrence of missing data is not random. So in this case, for example, if we have a data set like the one below, it is said to be a missing data pattern if, let's say we're going to take this missing data from A4 to A7. So basically, if the variable, let's say A3 is observed, or if the variable A3 is observed for a particular scenario, this basically implies that all the previous variables are also observed. So in this case, should have actually made a change. But basically, we're saying A2 should be observed as well for row 4, according to the monotone missing data pattern. So A2 should actually be observed for row 4. So we basically say if A4 is observed, or rather A3 is observed, then A2 and A1 are also observed. That's the monotone. So I just apologize. I had to make a couple of changes to this table actually. The monotone basically speaks to, if you check on the right hand side, A4, A5, A6, and A7, there's sort of a triangle of question marks that is formed. That speaks to the monotone missing data pattern. Now, so we've looked at what is it? What is missing data? Basically, data not available in your data set. We've looked at reasons why missing data could occur in your data set, of which there are several of them: failures in census and errors in the data entry process and the likes. So people just deciding not to provide the information as well. I know I do that when I'm filling in some forms. There are some questions which I actually think twice about filling in. So that will create missing data in a data set. Then we looked at some missing data mechanisms, so of which there were 4. So missing completely at random, missing at random, missing by natural design, and missing not at random. Then we looked at missing data patterns, of which there are 2, which are the arbitrary, so missingness, there's another word they like using. Missingness can occur anywhere in your data set, while the other pattern being missing, the monotone missing data pattern, basically says, okay, if a variable is observed, everything before is observed. If a variable is missing, everything after is missing. So that's basically the monotone missing data pattern. So having spoken about those, let's look at some traditional imputation techniques. Now, based on the scenario of the missing data, the mechanism and the data pattern or the missing data pattern, there are various data imputation techniques that currently exist in the literature and currently exist overall. So some of the techniques are like your listwise or case-wise data deletion, which we spoke about briefly, like looking at, let's take this table. Listwise or case-wise says, okay, I have 4 rows. Of course, my data set is going to be bigger than this, but then it says I have 4 rows. Now, row 1, A4 is missing. Row 2, A1 and A7 are missing. Row 3, A7 is missing. Row 4, A4, A5 are missing, which basically says, according to the traditional, those 4 rows I can delete. So we go from 4 to 0. So some of them, some of the traditional techniques are like your list-wise or case-wise data deletion. And then we move on to techniques which are more sophisticated in terms of what they use to do the imputation. They are more sophisticated statistically, and they also use more advanced concepts such as your AI techniques or technologies, machine learning or deep learning. These days, we're actually moving more towards deep learning techniques to handle missing data in our data sets. Hopefully, with deep learning, we can provide solutions to the last 2 mechanisms, which are missing not at random and missing by natural design. Hopefully with deep learning, we can actually provide solutions to that. So below, we're going to look at some of the commonly used missing data imputation techniques. So we're going to start off with simple methods like listwise and case-wise and move to more complicated and efficient mechanisms to handle missing data. Okay, let's take a look at listwise or case-wise data deletion. So which I've sort of demonstrated its drawbacks and its loopholes, and demonstrated reasons as to why you might not want to use an example like listwise or case-wise. Looking at this table again, if I'm applying listwise or case-wise, I basically go from 4 records to 0, because that's what listwise or case-wise speaks to. So if we check listwise or case-wise data deletion is a mechanism that will eliminate an entire row or record if there's any missing information. So I'll go again to our table. It deletes any row or record if there is any missing information. That basically says we're deleting everything here from row 1 to 4 because there's the presence of missing information. Now, it's a method that is the easiest, That's why people go for it, because instead of actually looking to impute, if there's missing data, delete the record. Most people go for it because it makes more sense, but then it affects the outcomes from the analysis, from the outcome from the data science task. So you ideally wouldn't want to do this, but then it's the easiest and simplest way to handle missing data. And it is also, like I've been mentioning, it's the least favorable option for the missing data problem, as basically any record containing missing data for any of the variables is discarded. I will go back again to our table. We're going from 4 to 0 if we are applying that technique. Sorry, I skipped that. So let's look, that's list-wise or case-wise data deletion, which we all agree is not the most favorable method or approach to use. Basically, you're saying if there's missing data in a row, discard or delete that row. So you see, it already reduces your sample size. It reduces the information you have to work with and process. The other one is pairwise data deletion. So it basically works by making the required analysis from the available pairwise data. So so basically, if we look at row 1, pairwise data deletion says, okay, if we look at row 1, A4 is missing, so we can just close our eyes to A4 and focus on A1, A2, A3, A5, A6, A7. But then the question which arises is the outcome one obtains from using just those records which are available enough? Is it going to make sense doing that? Because if we look at it, row 1, we used everything except A4. Now for row 2, we're going to use everything except A1 and A7, which are different from row 1. So would it make sense then doing that? The answer probably is no. I'm going to hear your take and your views on it. But from my side, I just think it doesn't make sense because we are not comparing apples with apples in this case. They are different. Row 1, we're not looking at A4, so we have a different data sample. We're using different data, we're using different variables to come up with an outcome. Row 2, we're not using A1 and A7. So that in itself is different from row 1. Because now we have, for row 1, we're using A1, A2, A3, A5, A6, A7. While for row 2, we're using A2, A3, A4, A5, A6. Different from row 1. So would it make sense using such a technique or an approach? So that is pairwise data deletion. So basically what pairwise data deletion in addition says is, pairwise data deletion implies that a row with missing data in one of the variables will be used only in calculation that do not require that variable. Okay, and that answers the question which was asked before. which was actually as before. So row 1, A4 is missing, row 2, oh no, let's not look at the monotone. Row 1, A4 is missing, row 2, A1 and A7 are missing. So basically, pairwise says, we're going to reduce, instead of records, the number of records, we're going to reduce the number of variables. So in this case, we're not going to consider A7 because there's missing data there. A6 is fine. A5 we won't consider because there's missing data. A4 we won't. But A3, A2 are fine. A1 there's missing data. So we're just going to use A2, A3, and A6. But then would using just those variables actually answer the question which you set out to ask, which you asked at the beginning of the task? Will using just A2, A3, A6 be enough to answer the question? Now, these are questions which we can ask ourselves again. And I'm happy this is data science. This is a data science workshop. So my fellow data scientists are going to I'll hear your views on that. But then would using A2, A3, and A6 be enough? Do you think it will be representative enough to get the outcomes required to answer the question which you asked at the beginning of the task? Okay. So that's another traditional method, pairwise data deletion. Then we have mean substitution, which was mentioned earlier. So basically it means substitution, we are basically saying, okay, for your missing data, we're going to take A4 again. We're just going to replace that missing information, the question mark, with the mean of the available data. So 63, 63, and 57. Another question, we could ask ourselves a question, is that enough? It might actually work better than listwise and pairwise data deletion, but still we're going to ask ourselves, is it enough actually doing that? Yeah, so if we look at A5, we can do the same. A7, we can do the same, even A1. So that will be 1929 divided by 3. Okay, which is more or less a decimal. 29 by 3, so 9.67. Now, if we replace, would that make sense? So those are questions which one can ask self when actually faced with such a problem. Would using minimum imputation or substitution be enough? So next we're going to look at median, which is another one that has been used. So there's mean, they've used mean substitution, median substitution, and on very rare occasions, there's actually been mode. Now, if we use median substitution, which is basically using the median of the available variable entries as the value of the missing information. So if we take A4 again, we have 63, 63, and 57. The median of that will be 63. So the missing information will be 63. Okay, perfect. Then you still ask yourself the question, okay, is that fine? Is it actually is it representative? Is it fine? Is it good enough? If we do for A7 using the median, So we have just two available. So 15 and 34. So we'll do 15 plus 34 divided by 2. And we'll use that. So that's 49. So that's 24 point. So I'll just round it up randomly now. So 49 divided by 2. Yeah. So 24.5. So does using 24.5 as the missing information make sense? That's a question you ask yourself again, looking at what is actually available. Does 24.5 make sense when there's 15 available and 34? So that's the median substitution. Okay, this is where I call on, I'll look to your brilliant minds again, having been through listwise or case-wise, pair-wise, the median substitution and the mean substitution. Now the question we can ask ourselves is, would using such techniques actually solve the issue? Now, I'll just like to hear your reasons, whether yes or no. Would just like to hear your reasons for why you think. I might have actually, I have my own view, which is, okay, maybe let me not give my own view and skew the findings from my fellow colleagues. But let's just hear what your views are. Would using these techniques solve the problem? And would just like to hear your reasons, whether it's yes or no. What's your reason behind it? Thank you. Prof? Hello? Okay, so like Prof mentioned, you can raise your hand or yourself, and you can also drop a comment in the chat function available. Okay. So I'm guessing everything is fine. Questions were answered.
There's somebody's hand is up.
Okay, all right, perfect.
Joel.
Okay.
Okay. Is an obvious answer on my side. It's an obvious answer of no. Because this method deletes some information or some data which carries some information that could be used in our analysis. So deleting them, using them will not solve the problem, will not solve the issue. So it's an obvious answer. Thanks.
Okay. All right. Thank you very much. Yeah, that's also the answer I have in mind. I don't think it will. I'm glad I'm not the only one who thinks that way. So thank you very much. Yes, Prof, is there anybody else?
No, Dr. Leke, I can't see anybody else that's hands up. I think that's it.
All right. All right. So now we're going to move from those traditional to what would be more advanced. Yeah, they are more advanced in terms of, okay, they're not, I'm just thinking about how to phrase it because we're actually going to look at advanced techniques. So your techniques that use artificial intelligence related concepts. So this is more, regression methods are more advanced in the traditional realm. Let me put it that way. So basically, regression methods say we generate a regression formula based on a case of complete data records for a specific variable. Now, for the rows in which there is a missing value, we just predict or approximate its value based on the regression equation which we came up with, based on the regression equation which depends on the currently available information in that record. So it is worth noting that in the regression technique, an equation is created for all the variables with missing values, with the other variables being basically dependent variables. So your variable with the missing information becomes your, as now your dependent, while those that are available become your independent variable in the regression equation. Now, the process to impute this missing information is repeated in a sequential manner for variables with missing information, which implies that for a variable with missing values, a model is fitted using the rows with observed values for the other variables. So we're going to see an example of how a regression equation or the regression method would work. So if we take, in this case, let's take, okay, row 4, where we have 32, 8, 18, 57, A5 is missing. There's 28 and there's 34. We can come up with a regression equation to impute A5 based on what is available, and that's the equation we've depicted. So A5 equal to A1 plus A2 A2 and so on. So using this technique to approximate the missing information in row 4, which is the example we mentioned now, will lead to the regression equation. Now, the fitted model that we see there with A5 being the dependent variable, so that fitted model includes the regression parameters, your lowercase a's, and it also has the error term, because it makes sense to add an error, because unless one says perfect imputation, but it makes sense to add an error, so you have a range, lower bound, upper bound. So that's what the error would do. So we have the parameter, the regression parameter is based on the error. So that would be the equation to get A5 for row 4. Now, if we look at row 3, but there's 14, 27, 63, 47, and 32, A2 is missing, A7 is missing. So we'll come up with a regression equation for A2, which has A1, A3, A4, A5, A6. And we'll also come up with a regression equation for A7, which has the available information, plus the error, of course. So that's the sequential part of the process that we mentioned before. So that is the regression equation, which makes more sense actually doing that. You can easily get more, you can get values which make sense based on what you already have in your data set. Now, the other more advanced traditional technique will be multiple data imputation. So multiple data imputation basically says, we'll take this table as an example again. So for row 1, A4 is missing. So we're going to come up with multiple estimates of what that missing value is. So that's multiple imputation. So basically create several data sets in which the missing data are generated that can be used to replace this missing information. And the data from the imputed data sets are then applied, and parameters for this are estimated and approximated based on, now we don't just have one imputed value, we have multiple. So you can come up with, you can either use, for example, the average of those 10 imputations as the imputed value for your missing record or your missing variable. So you can come up with different ways to actually come up with the missing information. So from this 10 imputations, I can either take the average of the 10 or whatever other statistic might be better served with serving. Yeah, whatever other statistic might be better to use. But that's the good thing with multiple imputation. You don't come up with one, you come up with multiple, and then you come up with a mathematical technique to end up with a missing data estimate or impute, which could be your average of the 10, or whatever else you decide to use, which makes more sense than just deleting the record and just using the mean of the available records. So this makes more sense. So it's a technique which basically combines popular statistical advantages of expectation maximization and likelihood with the well-known capabilities of the hot take imputation technique to generate these raw data vectors, which will then be used to impute or fill in the missing information. So this one already makes more sense. It minimizes, it sounds more like it minimizes the bias in your estimates. If you're coming up with 10 estimates for your missing data and then you're still using a mathematical or statistical approach to come up with one value at the end of the day for that missing information, that already sounds like you're reducing bias in your estimates. Now, multiple imputation functions by producing by producing a maximum likelihood based on the covariance matrix and the vector of means. And it's similar in a manner to the way in which expectation maximization works. So we're going to provide a reference if you want to read further on this. Because like I said, people have actually worked on missing data. It's a very important thing. It's a very important concept and topic to actually handle your missing data, as opposed to just using traditional, which, like my colleague said, it doesn't sound like the best thing, just using list-wise, case-wise, or pair-wise data deletion. Now, multiple imputation finds approximations for the missing data entries with the aim of making the data set complete, so we don't delete the record. And the main idea behind multiple imputation is to approximate the missing value by making use of an appropriate model that incorporates all the elements of randomness, thus minimizing bias in your estimates. It repeats the process, multiple times, whatever might be favorable for you. It could be 5, 10, 15. So, but it repeats the process in this case m times, where m is determined and defined by, in this case, the data scientist, and it generates m complete data sets with m different estimates of the missing information. It uses algorithms which are applicable to complete data sets. It carries out analysis of the data elements in each data set. It calculates the final value for the approximation by finding either the, so this is where you are free again to use your mind and find whatever works best. So in this case, we say it uses the average. So that it uses the mean from the, if we did 10 different data sets with 10 different imputed values, those 10 values divided by 10. So we can use the average. So we average the imputed values and use the average as the missing information. And then the last thing it actually does is compute the value for the standard errors by finding the average of the square errors from the m different data sets, whatever the number might be, while it's also calculating across the m samples for variance of these data sets. Okay, so in a nutshell, talking about multiple imputation, we'll just summarize all of this. So what we basically saying with multiple imputation is impute the missing value m times, whatever m might be, you decide. And then you can use whatever other statistical or mathematical approach there is to actually come up with one value for the imputation. And then in a nutshell, what happens in multiple imputation is you do it multiple times as opposed to just once. So you are trying to reduce and minimize biases in your estimates. Sorry, I'm going to come back again to you. I like the answer I already. I like the answer I got. So in a way, these questions are actually, the answers to those questions are in a way straightforward, but then they actually get one to think, which is the core, which is the main thing, which is important. So here we're asking, what is your view on regression methods and multiple imputation? And would you get a more representative imputation if you use any of these techniques? Thank you. So I'll just check. Please feel free. If you need to see my face again, just to know I'm a human being. So at least you saw the teeth. So because we're in the era of the fourth industrial revolution. So we have those two questions now. If anybody wants to. So we're basically asking, what is your view on regression methods and multiple imputation? And would a more representative imputation be obtained using these methods? All right, Prof, please let me know if you encounter anything. Or come across anything. I'm just checking as well. All right, so no one, okay. Oh, okay, Luke. Luke Joel.
We now have a better imputation now than just deletion. They represent, though there's a need to be sure that they are good for the problem at hand, but they are good enough to represent the imputation or to obtain imputation of the missing data.
Okay.
Thank you.
All right, thank you, thank you. Very important. So we're just going to take this table as an example. So basically what you're saying is, if we're looking at, let's take, row 4. So looking at that regression equation, we are most likely going to come up with a more representative value for that missing data in A5, right? Okay, so thank you very much. Yeah, so that's why we move from more conventional traditional to more advanced traditional. So your listwise, case-wise, pairwise data deletion, mean substitution, median substitution, and moved on to regression methods and multiple data imputation, because those data imputation techniques reduce as much as possible the biases in your estimates. So now we're going to look at advanced missing data imputation techniques. Because like Prof mentioned at the beginning, yeah, in addition to what she mentioned, looking at missing data is actually one of my main points of interest. I actually look at ways in which we can handle the problem of missing data in a more, for lack of a better word, I'll say realistic way. So looking at advanced missing data imputation methods. So we're going to go from K nearest neighbor imputation. So KNN, K nearest neighbor in itself is already, it's an artificial intelligence technique, which is based on, like the name says, K nearest neighbors. So we have K nearest neighbor imputation techniques, and we have other techniques which use machine learning and deep learning models. So the whole point of advanced missing data imputation techniques is basically to address the bias issue in your estimates. So regression methods and multiple imputation are already designed to address the bias problem. Now, this advanced techniques taking the addressing of the bias problem in your imputations further. So the first method we're going to look at is the K nearest neighbor imputation technique. And this technique basically, as mentioned before, makes use of the K nearest neighbor method to replace missing information in data sets. So it normally makes use of, so there are different distance measures. There's Monotone, and there's the Euclidean distance metric, which the K nearest neighbor algorithm, or the K nearest neighbor imputation algorithm to be more specific, makes use of. Now the Euclidean distance between 2 points is basically the length of a line segment between these 2 points. And mathematically, it can be expressed as we indicate or depict below as dpq equal to the square root of the square of the difference between p and q. So this is an imputer, which is actually a Python package. It's part of the scikit-learn Python package, to be more precise. So it actually addresses the bias issue in imputations in your guesses for the missing data. So this is a technique that actually addresses that aspect. So in addition to the K nearest neighbor imputation technique, so not sure whether to mention, but like I said before, I actually do quite a bit of work on missing data. So this is something which one worked on. And yeah, 2012, 2013, using autoencoders with swarm intelligence algorithms to do your imputation. Now we're going to see what autoencoder networks look like later on. Basically, it's a technique which makes use of an autoencoder neural network in combination with a swarm intelligence algorithm or technique to impute your missing data. So autoencoders are neural networks. Swarm intelligence will be the likes of genetic algorithm, particle swarm optimization, and colony optimization and the likes. Now, an autoencoder network, what is it? Basically, it's a network where the input and the output are the same. So in the architecture of an autoencoder network, the number of inputs equals the number of outputs. And then there's a bottleneck layer. So if you look at an autoencoder network, it looks quite a lot like a butterfly in terms of architecture. Now, if we say that's the autoencoder network equation, where X is the input, W are the weights, and Y is the output. So in an autoencoder, Y should equal X. So the aim is basically to minimize. In such a setting, you want to minimize the error between your output Y and your input X, because at the end of the day, you want them to be equal. So you need to minimize the error between one and the other. So like we mentioned, the aim in autoencoders is to minimize the error, which is X minus the autoencoder function. And ideally you want to, so we're going to look at the final equation, the last equation, which is in this case, I think is more appropriate because we have XU, which are the unknown input variables, and XK, which are the known input variables. So in minimizing, because the autoencoder network basically aims to replicate the input at the output. So the output has to be equal to the input. So the hope is in minimizing this error, you are getting representative estimates of your unknown, so your missing value. So that's what happens in this kind of imputation. And it actually got quite good results. I thought they were quite representative, but that sounds biased considering, yeah, I worked on it. It sounds biased, but I actually think it did. And next we are going to see that using even more advanced techniques actually does the job. So having spoken about autoencoder swarm intelligence imputation, then we actually have deep, so autoencoder, that's more your narrow autoencoders. So just the one hidden layer sort of architecture, we'll see that subsequently. But then later we have deep autoencoder and swarm intelligence again, which is using deep autoencoders and swarm intelligence, your genetic algorithm, your ant colony optimization, your cuckoo search. There are a lot of swarm intelligence algorithms out there, and new ones seem to come up with time. There's one on lions. There are a lot of them. So the difference between this technique and the one we spoke about before is in the architecture of the autoencoder. Like the name says, there's autoencoder versus deep autoencoder. Yeah, we'll see the difference in a picture. And the word actually speaks for itself. One is deep, and the other is just a narrow autoencoder. Now, the definition of deep differs. The definition of how deep differs. How deep the autoencoder network should be. So those are more advanced, your k-nearest neighbor, your autoencoder networks, your narrow autoencoder networks, and your deep autoencoder with swarm intelligence algorithms to do the imputation. Okay, so this is a narrow autoencoder. Like we said, it looks like a butterfly because the number of inputs equals the number of outputs. And then there's a bottleneck layer, which has fewer nodes than the input and the output. So it looks like a butterfly. Now that's a narrow autoencoder. Now a deep autoencoder, deep because it has multiple layers. So hence the difference in the architecture. One is just input output hidden. This one has input output, but it has 1, 2, 3, 4, 5 hidden, basically. So the difference is just in the architecture of the autoencoder network. So this is a deep autoencoder and this is a narrow autoencoder. Now, so here we just actually showing deep versus narrow. So if we look at the, should have put titles, but if we look at the bottom image, the top row basically shows digits with missing parts. So that's your missing information. For example, if we take 8, you can see there are black spots in your 8. Why? Because pixel values are missing. Now, if we look at the image at the bottom, that's actually a reconstructed image from using a deep autoencoder with swarm intelligence. In this case, we use deep and colony optimization to obtain that. Now, just my view, I think it did a pretty good job at reconstructing the image. Then the top image is actually using a narrow autoencoder with swarm intelligence. So at the very top, we're using a narrow autoencoder with particle swarm optimization. The bottom row is a narrow autoencoder with genetic algorithm. Now, you'd agree with me, besides narrow plus genetic algorithm not doing a good job at the reconstruction, it does include, it does bring in quite a lot of noise. So those white spots, they don't need to be there. If you look at the actual numbers, there are still missing pixel values. So the numbers are still incomplete. So narrow plus genetic algorithm didn't do quite a good job. Now the top one is narrow plus particle swarm optimization. It did a better job than the bottom row, but still, it looks a lot different from a deep autoencoder with a swarm intelligence algorithm. There's still noise. Some of the pixel values, not a lot, but some are still missing. But then that's just to show deep autoencoder versus narrow, deep with swarm intelligence versus narrow with swarm intelligence. So you can see that the deep actually seems to do a better job than narrow. And that's why I don't know if it's the general view or the general way of going about using data, but currently my interest is in actually focusing on deep learning methods to address missing data, because this already seems to suggest there's promise in deep learning than for such cases, because in this is more image processing. So there seems to be more promise in using deep learning for such cases. And it sort of speaks to, in general, deep learning might be the answer than narrow learning, or narrow learning. Let's go with narrow learning, because there are several algorithms which you can use in narrow learning. So that is what I had to present to you all about missing data. Missing data is very important in the data science fair, because it's part of the first processes being pre-processing of your data. You can encounter missing data there at that point. But then knowing how to actually handle the missing data, knowing the mechanism, knowing the pattern, knowing how to handle the missing data, just feel it's actually important. And it's going to help in the decision-making process, in the reporting. The outputs are going to be quite representative. Oh, thank you. Yeah, we have a couple of references which we included in the presentation. I think these are pioneers, as mentioned before. These are people who've worked on missing data, because they identified missing data is important. It gets overlooked because we have traditional. If there's missing in a row, delete that row. But it doesn't answer the question, which you might have said at the beginning. I'm sure there's a better way of handling that missing information. Oh, thank you very much. We'll put the references, but for now, we have Q&A. but I'll just leave the references there for if you want to take down.
Thank you very much, Dr. Leke. To the audience, are there any questions, any comments, anything you'd like to pose to Dr. Leke?
And I should have actually dropped my email as well. As if you want to have a conversation around this, please feel free. But I just feel missing data is important.
Yeah, I agree.
It's very important.
Yeah. Tato has his hand up.
Good morning, greetings.
Morning.
Greetings. Morning.
Yes, with regard to the intelligence systems currently that are moving with the swarm intelligence, or if I may call it the meta heuristics. So with regards to meta heuristics and intelligence systems, in making sure that the inputs will produce the result, the required result in terms of the process, the concurrent process of the algorithm. So how do we make sure with the optimization process that the desired result will be reduce the computational load effort in maximizing the output, but also reducing the cost of the missing data? Because of my question is coming from looking at the data science, that majority of organizations spend much money in cleaning the data. So the cost of computational of cleaning data is more expensive than actually running the process with those swarm optimization intelligence. So how do we reduce the cost of computational cost using this method of meta heuristics or swarm intelligent optimization to reduce the computational load and the cost of cleaning that data, to make sure that our decisions are sound and they are more effective in terms of reducing the risk involved in implementation? Thank you.
All right, thank you very much. So how do we use meta heuristics to actually reduce cost? Because I like summarizing things. Oh, so apologies if, but did I summarize your question correctly?
Yes, meta heuristics also include the swamp intelligent optimization, swamp intelligent bee optimization, evolutionary algorithms, and then a genetic algorithm. So it's all this all algorithms that are optimizing the process to give sufficient or close to k nearest results that are matching the input and the output. So those algorithms, how do we reduce the computational load and the cost of cleaning the data?
Okay, thank you very much. So I guess to answer your question, one just has to find a trade-off, because implementing some of this, some of them actually take time. I've implemented one. I remember when I ran some of the experiments, they ran for 2 weeks. And then I was using just your normal Dell i3 desktops. So it actually took 2 weeks. But then I was just thinking, if I got a cloud and I ran those processes on a cloud instance, it will actually be cheap. And those processes are going to run faster. So it's just finding the trade-off between how much one is willing to spend, how quickly one actually wants to get, and the good, I guess I'll call them good results for now. But then finding the trade-off answers the question. Like finding the trade-off is the solution. Like for such a meta heuristics, you also need to find, they are quite nice, but then they're not, well, this is a personal point of view. They're not applicable in all settings and all areas in every domain. Need to find the one that works best for that specific application area, the specific domain. But to answer your question, yes, meta heuristics can be used to optimize cost, but then trade-off has to be found. In terms of, you need to actually see what you need to weigh up. Yeah, you need to weigh up what cost versus output. So I don't know if that, Prof, do you want to add on?
No, I don't want to add. I think you answered the question well.
Okay.
There is another question from Luke.
Yes, Luke.
So,
Okay. I just want to ask. Thanks for the talk. I just want to ask: are you using this swarm intelligence as a single base imputation, or as a multiple base imputation, or as a multiple imputation? You also, that is one. Okay. Hope you got that right, sir.
Yes, I did.
Oh, okay. Now, okay. Then the second one, you put KNN as an advanced imputation, and then that shows you put it before, after the multiple imputation. Okay, why in the literature multiple imputation has been found to be good, to fit into so many scenarios of imputations. Okay.
Okay.
Why did you do that?
Okay, thank you very much. So to answer your first question, single or multiple, it was single because like I mentioned before, used swarm with deep autoencoder. So at this point, I just investigated, okay, single imputation, is it going to do a good job? Is it going to be less, is it going to address the bias issue, which I think it did, considering the reconstructed images. So it was single. Now to answer your second question, why did I put KNN under advanced? So I don't know if you recall, because like I mentioned, so there's I've forgotten what I call them, but there's the traditional, there was a sequence. So we went from least to pair to mean, median. So there was a sequence. Now multiple imputation before KNN, multiple still fell under traditional, reason being it's considered a traditional. That's why there's a lot of literature around multiple imputation, because it's been around. Now, K nearest neighbors under advanced. One, K nearest neighbors is more artificial intelligence. It's more of an artificial intelligence technique. That's why it found itself under advanced. And also, it found itself under advanced because K nearest neighbor imputation actually, like multiple imputation, but more so addresses the bias issue. So I don't know if that answers your question. And hopefully I answered your 2 questions, because I remembered simple, multiple, and why is KNN under advanced. So KNN came after multiple imputation, reason being, multiple is under traditional because it's been around. And like you said, there's literature around multiple imputation. It's been around. That's why it fell under traditional, while KNN fell under advanced, reason being what KNN is actually. It's more an artificial intelligence technique or method. So I don't know, hopefully that answers. And Tato, hopefully I answered your question as well.
Thank you, Dr. Leke.
Thank you, Prof.
Are there any other questions, any comments? Dr. Leke, if you'd like, you can actually put your email address in the chat for those that might want to get more information from you regarding this. Please, for those of you, if you need more information, if you need any access to the links, I've provided the link here in the chat. So the recordings for each day will be provided there by the end of next week. For the first 3 days, they're already there. So you can go through those presentations if you want to. If you'd like to contact one of the lecturers that have presented, or you'd like to discuss more details with them, you can contact me if you don't have their email address, and I will put you in contact with them. I'd like to also just once again thank you, Dr. Leke, for this presentation. I think it's an extremely important topic. So I'm really glad that he was willing to present on this. And yeah, I hope that we will see you all tomorrow for our last day of this student workshop, where Professor Suvendi Rima will discuss, will actually provide an introduction to Azure Machine Learning Studio. So I hope to see you all there. Have a pleasant day, everyone.
Thank you. Bye.
You.